there's this unit that causes, well, confusion amongst physics students, and that's the electron volt. This is contained in A level of physics, and in this video you're going to learn about the electron volt, and you'll be able to solve some problems on electron volt. Now the thing is, you would come across this under electricity and magnetism, and you will come across it under nuclear physics. Okay, especially when you are studying photoelectric effects. Okay, so the electron volt is a unit which is commonly used to express very small energies. All right, so we have energy measured in joules. Now let's set the standard as 1 joule. The energy that an electron possesses, what if I tell you that it's way lesser than 1 joule? In fact, is when you look at it, quantum energy actually operates in small quantities, that is smaller, way smaller than 1 joules, and you see that in the next few slides that I'm going to touch. So the electron volt is derived from the definition of potential difference. That's the formula you have here. Potential difference, which is equal to the energy per unit charge, and that is the major equation that we're going to play around. So if an electron with a charge of 1.6 times 10 raised to the power of minus 19 coulomb. Now that figure you have here is actually a standard for the charge of an electron, so it's something you should know. So when that electron travels through a potential difference of 1 volt, when we say potential difference, it means when you have like 2 points in a circuit, A, B, and the potential difference between these 2 points is 1 volt. You see that as we move along. So that's we just rearranged this formula to give you this. That's your QV, that's your charge times the potential difference. So you have the charge as 1.6 times 10 raised to the power of minus 19 coulombs multiplied by 1 volt. That is the charge moving through 1 volt of PD, and that will give you the energy of 1.6 times 10 raised to the power of minus 19 joules. And for 1 EV, that's how we write electron volts. So 1 EV is apparently equal to 1.6 times 10 raised to the power of minus 19 joules. That was just what we got here. So it's more like we just replaced the whole thing. So when a charge moves through 1 volt of PD, this is the energy, and that's what led to the measurement, electron volt. So since we've talked about movement, okay, the electron moves from rest. That means a type of energy has a big role to play in that, and that is kinetic energy. So it says here that if an electron has arisen from rest, an electron volt is equal to the kinetic energy gain. So the electron volt we talked about is equal to, so you can say that's EV equals to kinetic energy, and this the formula for kinetic energy. All right, so if we are to bring this here, our goal here is to make the speed, that's the velocity, the subject formula. So how are we going to do that? So first things first, let's multiply both sides by 2. So this will be mv squared. Then you divide both sides, by m. Or we can just flip this guy here. Okay, then you do v squared equals 2ev divided by m. Then you make, remember we're making the velocity subject to formula. Then you take the square root, that's 2ev divided by m. That's 2 electron volts divided by m. That m is mass. You have that in square root. So that's what we got here. Okay, so here's a question for you. It says show that the photon energy of light with wavelength 700 nanometers is about 1.8 electron volts. First and first, nanometers, okay, is within the range of 10 raised to the power of minus 9. So you should take that into consideration when you're doing your working. So go ahead and pause this video. Now, first things first, we know that our wave equation is v equals f lambda, that's your velocity, equals to the frequency multiplied by the wavelength. Okay, so in this case, when we're working with photon of light, we just change the velocity here because we know the value that we need. That's, we change it to the velocity of light. That becomes c equals f lambda. Then we go ahead to make f the subject to formula. That would be f, that's your frequency, equals c over lambda. Okay, and then you have your energy equation, which is equal to your Planck's constant multiplied by the frequency, and we already have the frequency as c over lambda. So what you do is to substitute. Yeah, that's what we do. You substitute. Now be E equals the Planck's constant multiplied by this guys right here. That's a frequency. Okay, so the next step is substituting the values to calculate the photon energy. So we need to get the amount of the energy in joules. So we just substitute the values. Planck's constant is 6.63 times 10 raised to the power of minus 34. Then the speed of light is 3.0 times 10 raised to the power of 8 meters per second. So then we divide by the wavelength. We're already given the wavelength as 700 nanometers, and that will be times 10 raised to the power of minus 9. So that will be 700 times 10 raised to the power of minus 9. So that should give you 2.84 times 10 raised to the power of minus 19 joules. Okay, so the next thing we have to do is to convert the photon energy. We have it in joules, so we need to convert it back to electron volts. And 1 eV is equal to 1.6 times 10 raised to the power of minus 19 joules. Okay, so if you are to, this is if you are to convert from volts to joules, that means we multiply it by this value right here. Now if we are to convert from joules, like what we have here, to electron volts, so we divide. So that's just what we're going to do. So that's 2.84 times 10 raised to the power of minus 19. Oh, this is 9. Divided by 1.6 times 10 raised to the power of minus 19. So you have 19 cross out each other. That is 2.84 divided by 1.6. If you punch this into your calculator, your energy will be 1.78 electron volts. So thank you guys for watching. If you have questions, just drop it in the comment section and we'll attend to them.